Okay, so hello everyone. So welcome to our this week Progress in Efficient AI seminar talk. And today, we're pleased that we have the Dr. Meng Li from the Facebook who gives a talk on the title with the efficient audio visual understanding on AR devices. And Meng is currently a senior AI research scientist with the on-device AI research in Facebook Reality Lab. Previously, he received his PhD degree from Texas Austin. The supervision Dr. David Pam. His research interests include the neural architecture search, AI software hardware co-design, privacy preserving, ML. Dr. Li was a recipient of the UT Austin Outstanding Dissertation Prize, the EDA Outstanding Dissertation Award, and the first place in the grand final of ACM Student Research Competition, as well as the Best Paper Award for the host and the GSVSI. So now let's welcome Dr. Li to give us a very exciting talk.
Cool, thanks for the introduction. Just to make sure you guys can hear me well, right?
Yeah, we can hear you.
Okay, great. So hello everyone. I guess like good afternoon for the East time. And my name is Meng Li, and it's a great pleasure for me to be here and give this talk. Today, the topic of my presentation is efficient audio-visual understanding on AR devices. So today, we are able to dive into a vast ocean of virtual information provided by the two-dimensional surfaces whenever and wherever we go. However, it should be noticed like this 2D surfaces like cell phones may not be the most natural way for interaction. In fact, in many cases, due to a lack of sufficient interaction between the virtual and real world, sometimes this 2D surfaces can be disturbing and even keep someone isolated from the real world. So one natural question from us is, what should an ideal surface be like? And so like, look at this figure, like it's a like glass. I guess many of us, including me, are wearing the glass right now. And a glass can enhance our the acuity of our vision system every waking moment. But what if this is an AR glass, right? That can enhance our perception in many other ways as well. Specifically, what if this is an AR glass or that can provide us with augmented reality, virtual reality, and everything in between? What if this is an all-day wearable device that can provide us with contextualized and relevant information whenever it is needed? So in fact, it has been predicted that instead of wearing carry your cell phone every day, like in the future, people will wear stylish glasses. These glasses will offer you virtual reality, augmented reality, and it will be all-day wearable. And the distinction between AR and VR will eventually vanish, and the virtual and the real world will just mix and match throughout the day according to our needs. So what can an AR glass enable us to do, right? And I think maybe we can imagine this together. So what if an AR glass can enable us to see better in the dark, can provide us real-time translation, and also can remind us when we cannot remember someone else's name? So like for the last use case, when we are in the in a crowd of people, of course, what we don't hope is there are like thousands of naming tags like floating all around, right? But we also don't want to explicitly submit a query to the glass each time when we need such functionality. And what we want is really like, we just want the name tag to pop up whenever we need it, the same way as our own memory, right? And it will take always on and context aware AI to make this happen. As a good analogy, I think you can think of AR glass as a tiny assistant with a perfect memory and internet connection sitting on your shoulder, always ready to answer your questions and proactively providing you with useful information. So what are the technologies that are needed to achieve this vision, right? Let's again use the same example to think through the technologies that are needed. So first of all, we need a high resolution display that is bright enough to be visible even in full daylight. Also, we need the context awareness so that the AR glass can understand who are the people that we are currently interacting with. We also need image recognition to associate an individual with the image. And we need the graphics to render the annotation. We need word locking to attach the annotation to a specific person. Also, we need depth sensing to handle the possible occlusion between the virtual and the virtual object and the real people. And as you can see, just to enable this seemingly very simple task, there are so many technologies to perform. And also, it should be noticed that to deliver the best user experience, we have to deeply understand the user intent from the context. So there are at least the following requirements for an AR glass. First, we need this glass to be socially acceptable. This basically means the glass not only need to look nice, but also have all the privacy preserving components ready. Also, we hope this glass to be lightweight so that we are able to wear them all day. Also, the glass needs to have all day battery life, even at the form factor of a glass. And last but not least, for everything that touch your skin, it has to be highly thermally constrained. All these challenges actually require significant innovation from different aspects, including optics and displays, audio, interaction, computer vision, artificial intelligence, system design, and UX. And over the last several years, with the rapid development and evolution of artificial intelligence, it is playing a more and more important role that will have a profound impact on all the elements of an AR glass. So while AI is super important, we further argue that most of this AI workload actually need to run on the device for the following reasons. First and foremost, as the AR glass keep processing the audio, video, and the biometric signals, we need to provide the most relevant information. We need to make sure all the signals are well protected for user privacy. According to the recent user study, on-device execution that keeps your data local is the best perceived way for privacy protection. Secondly, on-device AI significantly reduce the reliance on network connectivity and makes AR more accessible in many different situations. Meanwhile, on-device AI also has the potential to significantly reduce the latency and energy of the system by avoiding the round trip through the wireless. While on-device AI for AR is super important, it is in fact not an easy task. And to understand the challenges, let's first take a look at the applications that we need to deal with in AR to realize our vision. Specifically, we roughly compare these applications from the following 4 aspects, including memory bandwidth and computation intensity per inference, latency sensitivity, and usage frequency. First, for audio and language related workloads, like automatic speech recognition, text-to-speech, natural language understanding, etc. The model size is already large, and therefore the memory bandwidth requirement per inference is already high. Also, these models most of the time will be activated only by request. Therefore, the usage frequency is fairly low. In contrast, for AI-based depth estimation, because we need to keep running this depth estimation for fairly high input resolution at low frame rate consistently. So the computation intensity can be even higher compared to an ASR model. And the usage frequency as well as the latency sensitivity for this application is also higher. The third application is eye tracking, which is super important for AR glass. because humans' eyeball can move super fast, like we already have very high requirements on usage frequency and latency sensitivity, which means we need to run this model at high FPS with high latency constraint. And for this purpose, the eye tracking model usually work on a fairly low resolution input, and also it uses very cheap convolution operations. And therefore, the computation intensity and memory bandwidth per inference is much lower compared to depth estimation or ASR applications. We also have other applications, including hand tracking, including keyword sporting, and so on and so forth. And all these models have very different properties and characteristics, which demonstrate the high heterogeneity of the application. So based on the description of all the AR applications, we now can summarize the challenges for on-device AI in AR, mainly from the following two aspects. First, from the application level, we need to support heterogeneous applications. And many of these applications require no user perceivable latency for us to support processing high resolution input data like images or even videos. From the system level, because of the limitation of the glass form factor, even compared to the efficient mobile setting, we still need 1 or 2 order of magnitude again, because of the limit of the glass form factor, we already suffer from limited compute, storage, and limited bandwidth to the system memory. So to understand how we can deal with these challenges, in the rest of my presentation, I want to use video understanding as a concrete example to explain our efforts at different levels from application to hardware. So video understanding is a novel AR experience that helps to understand user activity and the environment. Video understanding tasks takes continuous input frames, sometimes high resolution as an input, and can help to understand users' activity and the environment. Here, on this slide, I show 2 examples. On the left-hand side, like this, this basically shows we can understand what the user is doing right now, like playing basketball or surfing or playing guitar. Right on the right-hand side, this is an example that given a video, you can localize different people in the scene and also understand what they are doing. And based on this information, video understanding can provide us with personalized, proactive, and context-aware assistant. Enabling on-device video understanding with high accuracy and high efficiency is actually not trivial. And because of the following reasons. First of all, compared to images, annotating video data is already much more labor intensive, which means we already have much fewer annotated video data compared to those images. The second challenge is on the video modality itself. Video modality usually means your camera needs to keep capturing the input frames, and you need to keep transmitting the data from the camera to the SoC. And this will incur very high system cost. And the last challenge is nowadays we know the resolution of the sensor are becoming higher and higher. And this continuous high resolution inputs usually makes the video understanding model much more computationally intensive and memory intensive. And to deal with this, these challenges, I think we luckily we have like different levers, right? And first, to deal with the problem with limited label data, we extensively study different data augmentation techniques and even leverage self-supervised learning to pre-train the backbone so that we only need a few annotated data to fine-tune the backbone for a specific task. In order to reduce the system cost for video modality, we already consider multi-model analysis and cascaded inference to improve the to reduce the latency and also improve the accuracy of the model. And in terms of the high resolution model inputs, we already leverage what we call hardware-aware model design to reduce the cost and also efficient compilation of multi-stream models. In the rest of my presentation, I will discuss this different aspects in detail. So the first technique I want to talk about is data augmentation that can help us to deal with a limited data set during the training. Data augmentation is actually quite widely used for both images and the videos because it can increase the effective data size and promotes diversity in training samples to help improve the model accuracy. However, one thing we noticed is previous data augmentation, like for example, shown here, the grid mask of data augmentation, is usually just applies augmentation to the full image. And sometimes this can destroy the key characteristics of the original images. For example, here, the grid mask actually masks the chicken, right? And in this way, the augmented samples that you generate may actually have ambiguous labels. And this may hurt the network training, especially for small networks. And what we propose is to improve these data augmentation techniques by always keeping the important regions untouched during the augmentation. Specifically for video understanding, we can always use motion-based saliency map to detect, okay, what are the moving objects in the scene. And then we only apply the augmentation to the background. And as shown in this comparison, with this simple improvement, we can further increase the accuracy of this large model by almost 0.4%. And in fact, what we found in our internal workload is for small models, such improvement can be even larger. And this paper is published in CVPR 2021. The second technique we can leverage to mitigate the training challenge is on self-supervised learning. Self-supervised learning, the basic idea is to leverage vast unlabeled data to pre-train the backbone. And previously, I think like a conventional self-supervised learning scheme used like contrastive loss. Essentially, you want to train your backbone to encourage like similar or to extract the similar representations for different views of the same object and the different representations for different objects. And what we find is we can further augment this contrastive loss by adding both spatial and temporal tasks. Here, spatial and temporal tasks is basically to encourage the backbone to understand more on the spatial arrangement and temporal information of a scene. Examples could be for spatial tasks, you can tile the input images and then rearrange the tile in the image and ask the backbone to recover the original image. And in terms of the temporal task, we can actually temporally reorder the frames in the video and then train the backbone to recover the correct order or sequences. And as shown on the right-hand side for the comparison, by adding the spatial and temporal tasks, we are able to increase the network accuracy by more than 6%. While we talk about the training challenges, for the deployment challenges, like video understanding is also, from the deploying point of view, video understanding is also quite challenging. As I explained previously, this challenge mainly comes from two folds, including the camera side as well as the inference side. So on the camera side, to capture input frames continuously, you're leads to like hundreds of milliwatts power consumption. And if you think about it for an AR glass, your total power budget is around like it's like several hundreds milliwatts. And this includes everything, including camera, display, and so on and so forth, right? So this camera cost to support video understanding is actually quite significant. once you capture this data, you also need to transmit the data and store this data, which will add further cost and accelerates the battery drain. In terms of the network inference, because like you are dealing with high input resolution frames continuously, right? Video understanding models are usually quite expensive. It usually takes like hundreds of gigaflops to understand the user environment and actions, which is actually 10 to 50x more expensive compared to models operating on single images, like the ImageNet models. How to reduce the camera cost and the inference cost becomes quite important to deploy this video understanding application to the device. So what we do is we follow a multi-model approach. Essentially, instead of using an always-on video understanding pipeline, we try to use cheaper modalities like audio or IMU as a trigger to the more complex video understanding pipeline. Like audio capture is usually several orders of magnitude cheaper compared to the video processing. And also transmitting the audio signal is also much more efficient. And sometimes because the audio model is so small, we can actually push this to extreme in the sense that we do near sensor compute, which means the compute happens at the exact same place where the data are captured. And this can help significantly minimize the system power cost. And with the help from the audio and IMU signals, the complex video understanding pipeline is only activated when it's needed or when it's have to. And on the right-hand side, we show an example. This is from a paper named "Listen to Look" from Facebook AI research. Essentially, the audio signals are used to select the frames from a video clip, which are then sent to the video understanding pipeline to achieve significant reduction of the model computation. So for the cascaded approach with audio and IMU and the video, like it looks like, the pipeline looks like below. First, we have always-on audio pipeline. This pipeline will always listening to the users and detect important transitions that are predefined. And once such transitions are detected in user environment, then a single image-based pipeline will be activated. And this pipeline will detect the important objects in the scene. And one, for example, basketball in this case. And once such basketball is detected, the full video understanding pipeline will be invoked and to detect to classify the user's action, including whether you are currently blocking, dunking, dribbling, and so on and so forth. And as you can see in this pipeline, the third stage is the most computational. It's only activated whenever it is needed. And the always-on portion of this pipeline, which is audio-based processing, is actually much more lightweight. This multimodal approach not only helps with the efficiency of the pipeline, in fact, it also helps with the accuracy of the pipeline by improving the generalization of the model. Here on the right-hand side, we show a paper from Facebook AI research called Audio-Visual Slow-Fast Network. Instead of just taking one video stream as an input, this network actually takes 3 different streams, including a low frame rate video, a high frame rate video, and a high sampling rate audio as an input, and encourage the feature fusion throughout the network. And the ultimate purpose is to provide the most accurate video classification. And in fact, as shown in this paper, with the addition of the audio signals, the accuracy of this model can be improved significantly. Especially for those unseen test categories, we can observe a significant improvement in terms of the model accuracy. So far, we have been focusing on algorithm level techniques that can help improve the model accuracy and efficiency. Now I want to switch gear a little bit to discuss the hardware side, basically what we can do to on the hardware side to enable this efficient on-device video understanding. Right now, like nowadays, for mobile SoC, I think neural network accelerator is actually widely available. And it is usually integrated in the SoC as shown here. Usually you have a monolithic accelerator hooked to the system NUC, different IPs, including speech, vision IPs, and system memory application processors, all connected to the same NUC and will invoke the accelerator whenever it is needed. However, as we mentioned, the applications are quite heterogeneous, which means it is very hard for you to design one single accelerator that can achieve good performance on all these different applications. Therefore, what we are proposing is a more customized SoC, which encourages a more or a deeper integration of the speech IP and the network accelerator itself, as shown here in this figure. For each vision IP and speech IP, there will be a dedicated neural network accelerator. This neural network accelerator will be highly optimized just for this type of application to cut all the unnecessary corners and achieve the best performance and achieve the best accuracy per joule. And this scheme also help with resolving the memory bandwidth contention. In this original case, like all different IPs needs to talk to the neural network accelerator through the system NUC, right? And as we all know, network connections is becoming more and more expensive. And with this customized SoC, like we can make sure all the data actually remains local as much as possible inside this IP and significantly reduce the memory bandwidth requirement. So for AR glass, efficient hardware can help us actually to resolve like many of the challenges we have discussed. For example, for heterogeneous applications, we can design heterogeneous accelerators. For a high latency requirement, like we can design our accelerator such that it is friendly to small batch or streaming processing. For high resolution input data, we can customize the processing data flow, like the tiling and the ordering of the operators for this customized accelerator. And from the system level, when we faced with all this like requirements on limited compute storage bandwidth and higher energy efficiency, if we believe just doing network or hardware architecture optimization separately is not sufficient. And we need a paradigm shift by doing hardware and software co-design. So here is a figure that illustrates the high-level idea for hardware and software co-design. Essentially, it is a closed loop that consists of two major components, including the hardware-aware network design and the AR customized neural network accelerator. And the ultimate goal is to achieve higher accuracy, lower latency, higher efficiency, and smaller memory footprint. Previously, we have already talked about what does AR customized accelerator look like, so especially talk about the heterogeneity for this accelerator. And now we focus more on the hardware-aware network design part. So neural architecture search is proposed to help automatically optimize the neural network for best accuracy, given a bunch of constraints on flops, latency, and number of parameters for a variety of backbones. For a variety of backend hardwares. And it has been widely used for the hardware-aware model optimization. Since NAS is first studied back in 2017, over the last several years, NAS have been improved quite a bit. On one hand, as shown in this figure, given a fixed compute budget, the accuracy of the networks gets improved quite significantly. On the other hand, the search efficiency of neural architecture search also gets improved by orders of magnitude, from tens of thousands of GPU hours to around hundreds. Popular NAS method can be classified into three categories, including the black box optimization like NASNet, MNASNet, ABNet v3, or differentiable methods like DARTs, proxyless NAS, fair NAS, or weight sharing NAS like Big NAS, one-for-all network, and AlphaNet, which is proposed by our group. Weight sharing NAS builds a supernet that assembles all the network in the search space, and it is becoming more and more popular in recent years, especially because of its high search efficiency and the superior accuracy of the acquired networks. By building a supernet, first, like weight sharing based NAS can simultaneously optimize all the networks in the search space. And this basically gives the potential to significantly reduce the search time. Weight sharing NAS usually have like two stages as shown in this right figure. The first stage is the supernet training stage. Basically, the supernet as well as the subnetworks are jointly trained to converge. And the second stage, as shown here, is the searching stage, during which the networks with best accuracy, given different constraints, are selected. Ideally, for the weight sharing NAS, there is no fine-tuning or retraining that is needed, which leads to great search efficiency. For weight sharing NAS, there are two major challenges. The first one is how to customize the search space, which is also definitely shared with other NAS methods as well. And the second challenge is more specific to the weight sharing NAS, which is how to train the supernet efficiently. So for the first challenge, when defining the search space, we believe it is important to consider the property of the task and applications that we are dealing with. Here, I show two examples of visual recognition tasks, like pose estimation and semantic segmentation. This is also quite important for video understanding as well. But here, I just use single frame as an example to illustrate this. The main challenge here for this task is like as you can see in the figure, the person close to the camera is usually much larger in size compared to those away from the camera. And for the large object, to actually do the pose estimation or segmentation accurately, global context is more important. While for the small objects, we actually need detailed local information. And how to efficiently accommodate the scale variance and simultaneously both global context and local information is still an open question. So prior art method find it useful to of different resolutions. For example, like HRNet dynamic routing. We propose to explicitly search for the best network topology to encourage the multi-scale feature fusion. Our search space is shown in the figure here. Compared to the previous search space, we have the following key features. First, our search space includes parallel branches to simultaneously extract multi-fusion feature. And we also have the cross-scale branches, which can encourage the feature fusion for features of different resolution. And as shown in this red figure, on both semantic segmentation and pose estimation, we achieve much better accuracy compared to the previous work, including auto deep lab, dynamic routing, or HRNet. And in fact, on pose estimation, we can beat all the previous methods and achieve the state-of-the-art results on several data sets, as shown in the paper with code website. So besides the search space, the SuperNet training algorithm is also very important and directly determines the efficiency of the architecture search, as well as the accuracy of the model that we can get from the architecture search. With sharing NAS jointly trains the SuperNet and its subnetworks to reduce the training cost, which is actually much more challenging compared to training a single network. The basic training procedure for SuperNet training is shown in this figure. So for each batch of the training data, the cross-entropy loss is first computed for this SuperNet. Then several subnetworks are sampled in the search space, and the output for the same batch of data for each network are computed. To help with the convergence of the subnetworks, instead of using the cross-entropy loss to supervise the subnetworks, the knowledge distillation loss is used. Essentially, the soft labels from the teacher will be used to supervise the subnetworks to make the convergence easier. And the model parameters are updated based on both the cross-entropy loss from the SuperNet as well as the knowledge distillation loss from the subnetworks. Oops, sorry. So for the SuperNet training, there are basically two important questions. The first question is, how do you sample the subnetworks during the training? And the second question is, how do you encourage the convergence of these subnetworks? To improve the sampling strategy, what we propose is called like attentive sampling. The baseline sampling strategy for SuperNet training is just like you randomly sampling in the you random sample in the search space. However, this may not be the most efficient way, especially because when we do the searching or in the searching process, we only care about the networks that are along the Pareto fronts, right? How can we take this intuition during the sampling process is actually quite important. And what we propose is something called attentive sampling, basically to focus the subnetwork sampling along the Pareto front. While this idea itself seems to be straightforward, one key question is, how do you identify the networks that are along the Pareto front very efficiently during the training? And we propose different methods to help approximate the Pareto front with different costs. And as shown in the right figure, with attentive sampling, we can beat all the state-of-the-art models. And this paper is published in CAPR 2021. The second technique we propose to improve the SuperNet training is a new knowledge distillation strategy. Conventional methods leverage the KL divergence to measure the distance between the teacher and the student network. And we find that KL divergence may not be the best metric. And in fact, it in nature leads to an overestimation of the uncertainty for the teacher output distribution. Hence, what we propose is a new distance metric named alpha divergence, which leverages hyperparameter alpha to explicitly balance the overestimation and the underestimation of the teacher distribution. As shown in this figure, we compare using adaptive KD versus regular KD. And as you can see, in pretty much all the compute spectrum, we can achieve better accuracy for the models or better Pareto fronts. And on this figure, we basically show a comparison between what we call AlphaNet, which leverages the alpha divergence with the other state-of-the-art methods. And as you can see, we can achieve quite significant improvement, especially for small models as shown here. We can also leverage this architecture search algorithm to help with the video understanding models. And this is the basic flow. We have the, basically for each NAS iteration, we have the hardware profiler that can help us to directly get the latency of running a certain model on the hardware, as well as the training part, which can help us to get the accuracy estimation. And based on this, we can iteratively search and select the video understanding models that can give us the best accuracy while satisfying certain latency constraint. And as shown here, like compared to the handcrafted data on video understanding, we can achieve either 1.5x latency saving or 1% accuracy gain. And just to mention here, even this baseline models are handcrafted. Like we actually use some sort of greedy search for this to tune the network hyperparameter already. But hardware awareness gives us the capability to further reduce the latency and improve the network accuracy. So one extra thing I want to talk about is the compiler support. So compiler tool flow is actually quite critical for efficient execution. On one hand, for compiler, it needs to support like state-of-the-art efficient network architectures and operators. This include, for example, the depth-wise and group convolutions that is widely used in MobiNet series or Inception networks, as well as the attention layers that is used for transformers. Compiler support for layer scheduling in multi-pass architecture, for example, the slow-fast network that we mentioned previously is also quite important. It can help us to minimize the activation speeding and also achieve significant performance and energy win by avoiding the DRAM access. Also, by avoiding the memory bottleneck, the latency can be improved accordingly. In fact, in our real experiments, we show that we can achieve almost 3x latency reduction for large video understanding models just by optimizing the layer scheduling for a CNN accelerator. So far, I have used video understanding as a concrete example to talk about all the possible levers we have and the directions that we are exploring inside Facebook to enable very efficient video understanding models. And to conclude my talk, I want to talk a little bit about the future directions. First, we believe the hardware and network co-optimization is very important. Right now, for the neural architecture search, what we search is the network topology as well as the layer hyperparameters. All of this are primarily focusing on the network itself. But in fact, for the accelerator, there are also important design decisions, including how much resource we allocate to the accelerator to the computer array, how much resources we allocate to the memory, and the network on chip, and so on and so forth. And in fact, we have in one of our DAC 2019 paper, we have shown that it is possible for us to parameterize the hardware and fold the hardware into the neural architecture search process to jointly optimize the hardware and the network and achieve much better accuracy and latency improvement simultaneously. The second direction is in sensor and near sensor computing. We all know data movement is quite expensive. And in the future, as the resolution of the sensor becoming more and more becoming higher and higher, this data movement cost can be even higher. And therefore, in sensor or near sensor computing that do the inference where the data is generated can help to get rid of a significant portion of data movement and becomes a promising direction. But of course, there are trade-offs in terms of, let's say, how large the model that you can deploy, how flexible the flexibility you have to change the model architecture or change the model operators, so on and so forth. And the third direction is lifelong online learning. When we deploy some model to the device, let's say for video understanding, it is possible that the user's habits can change over time. And for this model, it is important to acquire this new knowledge and also gets itself personalized just for the user so that it can provide the user with the best experience. And this online learning and lifetime learning is quite helpful in this case. But there are also challenges, including how do you prevent overfitting on a specific user data? And also when you learn the new knowledge, how can you make sure your previous training data are properly honored and your previous knowledge are well preserved instead of just got discarded like directly, right? All of these are challenges for like this online learning. And of course, there are also a whole bunch of supports from the OS level, from the hardware level that is needed for you to enable this on-chip learning, right? Okay, I think this basically concludes my talk. Yeah.
Thank you, Meng. Thank you very much. So very informative talk, and we learned a lot. The what right now the state of art industrial lab is doing. So any questions from the audience?
Yes, I have a question. So thank you for thank you for a very interesting talk. So I have a question regarding the hardware and software co-design for the neural network. So if we co-design the hardware specifically for a network architecture, but after a few months we have a better algorithm for a network. So can the hardware support the newer algorithm, or there's some limitation regarding the future update?
Yes, I think this is a great question. So essentially, this is a trade-off between the flexibility as well as like the efficiency, right? And really, like as we discussed, first we use heterogeneous accelerators, which means for a specific accelerator, we only optimize it for, let's say, a vision task, right? And then like even for vision tasks, there are, let's say, different flavors of the network, including, let's say, the ImageNet type of network using convolutions. There are also vision transformers that use, let's say, transformer networks, right? But if you really analyze this, you will find actually for this network, they actually share very common characteristics. And when you design your hardware accelerator search space, you need to actually explicitly consider these common characteristics, and to avoid that you over specialize your accelerator just for a specific network itself. But instead, you want to jointly optimize the network for, the accelerator for a family or a group of networks. Yeah. Does that make sense?
Yes, thank you. So to summarize, like when we design the hardware, we have some like leeway, some flexibility on the hardware itself too, so that future update will not interfere with the current hardware. That is also integrated in the searching process.
Yes.
Yeah, right. Thank you. Yeah.
I think there's another question in the chat box. So will near or in-sensor computing improve privacy if you give users and applications only access to limited metadata?
Yes, this is a very great point, actually. Yes, like near sensor or especially like in-sensor computing, if you only give the metadata instead of the original image, it actually help to boost the user privacy quite significantly. And in fact, even nowadays, like even we don't have in-sensor and near-sensor computing, we need to, we actually are very careful in like assigning, okay, for OS, what are the data that is acceptable from the OS level, right? And for many private information, there are like hardware mechanisms to make sure even the OS or other applications cannot access it. Yeah, but like the idea of using in-sensor computing to help with privacy protection is actually quite reasonable.
Any other questions from the audience?
I have a question. So I just wonder that I don't really quite understand the idea of the accelerator here. Can you generally include that? What is the like the basics from the accelerator, how it is working?
Oh, sorry, I don't quite get the question here. What do you mean by how it is working?
So I think that the accelerator things, I think this can be quite important here to make such a big model to work in portable devices. So and you spend a lot of time on the NAS network, right? So why do you spend so much time on the NAS network? Why is that so important in the AR glasses?
I'm not sure whether I fully understand your question. Like, basically, the accelerator is basically a piece of hardware that can run this, let's say, convolution operations very efficiently, right? But like you gain the efficiency by losing some flexibility compared to, let's say, general purpose hardwares like CPU or GPU, right? And for this reason, like it's not like all the networks can run on this accelerator efficiently. And the neural network architecture search is a way to help you automatically design the network that can run efficiently on this hardware. Does that make sense?
Yes. So what you mean is that the NAS network design is to utilize the hardware potential of the accelerator. So you need to have many different size of neural network and to automatically choose the best one, right?
Yes. So essentially, NAS is a way that can explicitly fold, let's say, the ultimate inference latency into the network optimization loop, right? So that when you design your network or optimize your network, you will explicitly consider both the accuracy as well as the latency as the metrics to guide the whole model optimization process.
Oh, so you can choose the best one based on the cases.
Yeah.
Okay, great.
Other questions from the audience?
Hi, is this hardware internally developed or using off-the-shelf components with the accelerator? What is the technology you are using?
So we design our own in-house accelerator.
Okay. Is it based on FPGAs? You're implementing on FPGAs, or is it like?
No, it's not FPGA, it's ASICs.
Oh, it's ASIC. Okay. Thank you.
Mm-hmm.
I think there's another questions in the chat box. What are the challenges when applying federal learning to the on-sensor and the near-sensor computing?
Well, this is like two concepts here. Like you have like federated learning and in-sensor or near-sensor computing. So I mean, both of this I would say are quite important for the AR glass. But right now, for the in-sensor and the near-sensor computing, what I talk about is primarily on the inference side, and the federated learning is, from my understanding, is more on the training side. And the main reason is usually to put things like on sensor or in sensor or near sensor, like usually you have very high constraint on the, let's say, the area as well as the flexibility of the hardware. And right now, I'm not sure whether it is realistic to support the training process, including both the forward propagation, the backward propagation, the parameter updates, right? That basically requires a much higher memory requirement, right? And but like in sensor computing is I would say is one way to protect user privacy during the training. During the inference. And federated learning is one way to protect the user privacy during the training process. That's my understanding.
Other questions?
Another question. So what do you think about the cloud computing? Like you just compute everything from the cloud and then just transmit that result to the glass when you can use something like a 5G network or something. Is that possible, or there's some problems behind it?
So It's definitely a promising direction. In fact, for some applications, we believe that may be the way to go. But it basically, from my understanding, is really dependent on the applications. For some applications that involves, let's say, processing your highly sensitive personal data, I don't think it's a good idea to actually send the data to the cloud and do the processing on the cloud and get it back, right? Just because of the privacy concern from the people, right? But for some other applications, for example, maybe you are playing a game and you want to do some rendering on the cloud and then streaming the content to the device, right? And that could be totally possible.
Okay. So that the problem is not from the techniques, but from the privacy, you mean?
No, I would say like there are all different kinds of challenges here. Privacy is definitely one of the biggest concern, and also like connectivity issue is another concern, right? Like which basically means for some fundamental techniques, for some fundamental technologies to enable the AR glass, you may want to run it on device so that the AR glass is more accessible in different situations, even when the network is limited, right? And also there are like latency and energy trade-off there, right? Like on one hand, for on-device processing, you need to process everything on the device. That could add some latency and energy overhead because you're already on the device, you cannot get the as powerful accelerator as the cloud, right? But if you processing the workload on the cloud, basically you have the round trip latency through the wireless.
Yes.
Right. So it's really a trade-off that you need to, like for a specific application, you need to analyze, right? And eventually choose the scheme that best fits the specific application.
Okay.
There's another questions in the chat box. So, what role will ad hoc networks play for multiplayer AR?
So I think this is a very good question, actually. And right now, I think the AR is still in a fairly preliminary stage for which this kind of like interaction between the users are not really well started. But I think I totally agree with you, like for in the future, like to make AR, like to unleash the full potential for AR glass, this kind of user interactions through this, maybe through some like ad hoc networks could be like a good direction. But right now, I don't think this is on the like on the radar, like for the next several years, just because there are so many fundamental challenges for to enable this product.
Is there any other questions from the audience? So if no, so actually I have one question for you. So,
Sure.
So in at the last slides of the talk, so you mentioned about some of the future direction and especially for the lifelong online learning. And so I was wondering, so what is the type of the specification constraint for this the online learning in the AR scenario? For example, so do we need like this kind of streaming in data and every time, so this the online learning is very small batch, like just the batch size is just the one or very few, or whether such online learning or the lifelong learning is actually we can tolerate that, so we can begin to learn the new update in like every 3 hours and so on. So what is the type of the scenario constraint here? Because
so
different setting will directly determine so the different training strategies.
Exactly. I think this is a great question, actually. And I don't think this has been like fully sorted out, honestly. And because as you mentioned, like different schemes actually have trade-offs, right? Like if you are using streaming data, basically means the pros is definitely you don't need to store the data. So the privacy concern with like data storage is actually alleviated. But the problem is like, how do you train the model? And also you have to train this model whenever you get this data, right? This is actually not trivial at all, right? And in contrast, like if you just store the data and then like just and then only do the training, let's say when you charge the device, that's another possibility. And for this case, you can just use like regular training techniques like batch based, like mini batch based training, right? But the problem is you need to store the data, and how do you guarantee this, like the privacy protection for this stored data is another thing. And if you further, I think just now someone mentioned federated learning, right? If you further consider, okay, there's possibility that you want like several users to jointly train a model, then like streaming may be even harder, right? Because I mean, different user may have like very asynchronized like communication, right? And how do you actually make sure everyone is like updated with the latest version and can aggregate the gradients like properly, right? Like there are like all different kinds of like challenges over there. So right now, I think this is really an open question. Yeah.
Thank you. So is there any other questions from the audience? Oh, I'm the last one. Okay, so again, thank you very much, Moon. So thank you very much for giving us this very wonderful talk. Yeah, I learned a lot, and I learned a lot from what right now is the industry is working on. Many interesting. You see, this slide shows the many interesting future directions. Yeah, and I
Thanks.
all the audience, they also learned a lot. So
yes, thanks for having me here. Yeah.
Okay, thank you. So this is the end of our today's seminar, and also this is our last Efficient AI seminar talk in this semester. So look forward to meeting with you again. So in this summer, we will continue our this seminar talk. So thank you again. Thank you, Mo, and thank all the audience.
Yeah. Thank you, everyone.
Thank you. Have a wonderful afternoon.
You too. Bye.